Hi, today we are going to talk about Castelnuovo contractibility criterion, also known as Castelnuovo contraction theorem. Before we move on to the statement of the theorem, let me recall some of the stuff from surfaces. Recall that if you're given a surface X, a projective surface, then there exists a unique pairing from the divisor class of X to the integers denoted as C dot D for any two divisors C and D. Now there exists a unique pairing like this which satisfies the following four conditions. First, if C and D are non-singular curves meeting transversely, then their intersection is nothing but the number of points that lies on the set theoretic intersection of these two curves. That is the number of points on C intersection D. The second property that it must hold is it is symmetric. And then you require it to be additive. That means if I take a curve which is union of two other curves, well, C1 and C2 can be same or different. In that case, this intersection number or this pairing is being distributed over the addition. And finally, it depends only on the linear equivalence class of D, of C. That is, or C or D, doesn't matter because it's symmetric. That is, if C1 is linearly equivalent to C2, then intersection of C1 should be same. C1 with D should be same as the intersection of C2 with D. And how do we show the existence of such a pairing? We define, so for the case where C and D are transversal, we define C intersection D to be the number of points on C, set theoretic C intersection D, which is nothing but the degree over C of the divisor LD. So C and D are curves. So you consider the line bundle corresponding to the divisor D, you restrict it on your curve C, and we know that we can talk about the degree of a divisor on a curve, and this is exactly that thing. When C and D meets transversely, then we define the intersection number or the pairing in the following way. And otherwise, what we do is we show that we can bring every other case to this case. For more details, please check section 1, chapter 5 of Hartshorne. So H will stand for Hartshorne. So we have seen earlier in the example of blow up recall how had we defined blow up. So if we want to define the blow up of P2 at the point 0, 0, 1, we define it to be the subvariety inside P2 cross P1, where let's say the coordinate of P2 is given by x, y, and z, and the coordinates of P1 is given by a's to p, then the blow up of P2 is defined by the equation xa minus yb. Give me a second, I need to check if it is a minus of yb or plus of yb. Sorry, there was a network issue. Yeah, so it is so the equation of the blow up. So recall that how we define the blow up of P2 at the point 0, 0, 1. We take the subvariety defined by xb minus ya inside P2 cross P1, right? And recall that we have seen before that if we consider the pre-image of the point 0, 0, 1, which is exactly the point where we perform the blow up, Then let's say we call this E, then this E has these special properties. Then E is special. Why is it special? It is special for two reasons. E turns out to be a rational curve, which in general, rational curve means it is birational to P1. Well, more is true. E is actually isomorphic to P1. And then the second condition that makes E special is its self-intersection is -1. So I want to give a definition based on these special properties. So I want to call a curve to be a special curve. I want to call a curve C to be a -1 curve if it satisfies the above two properties. Yes? Okay. So now that we have the ingredients we require to state the Castelnuovo contraction theorem, let me go ahead and write down the statement of the theorem. So what does this theorem say? It says that if you have a smooth projective surface, then and E is a -1 curve as defined above, then there will exist a birational proper morphism from x to another variety x1 such that the following property will hold. The first property is this morphism will indeed contract my -1 curve. X1 that we get by contracting this -1 curve will indeed be smooth. And the morphism that we'll get in this process will be blow up of this point in the variety X1. Okay, so the first question that comes up is, so let's try to prove this theorem. The first question that comes up in proving or even thinking about proving this theorem is, how do we think about producing such a mu? How do we think about producing such a x1 such that the following properties hold? Well, in algebraic geometry, whenever you want to produce a map or a morphism, you take help of linear series. Recall what a linear series was. Let's say you're given, so this is a little bit of digression, sorry, digression. So maybe I'll write it with some other pen. Purple. Okay, recall that recall that if you're given a divisor d naught, then you can define the complete linear system associated with d naught to be the collection of all the divisors d which are linearly equivalent to d naught and are effective. So what happens then is this linear system that you define this way is in one-to-one correspondence with the set where L is the line bundle associated with D naught. Well, some people also write this global section thing as H0 of X of OXL. Yeah, so whenever you're given a divisor, you can always define a linear system corresponding to it, which is the collection of all the divisors which are effective and are linearly equivalent to D naught. And we see that this is in one-to-one correspondence with all the non-zero global section modulo this equivalence relation when you call two sections to be equivalent if they are just a k multiple of each other, right? Okay. So then what happens is that how are these linear system useful in producing a map from X to something else? So there is this fun fact about this linear system that this linear system, complete linear system, are finitely generated. So let's say D naught is generated by S0, S1, dot, Sn. Then what you want to do is you want to define a map phi. Let me write D naught here because it's phi corresponding to this D naught. From X to Pn, where I send the small x to nothing but S0 of x is to S1 of x, dot, Sn of x. Right? Now, based on how D naught behaves, your morphism corresponding to the linear system of D naught behaves accordingly. That means based on how D naught is, P D naught behaves accordingly. For instance, if D naught is base point free, then P of D naught is a morphism. Let me explain my comment in here. What is base point free? So recall that we have defined the linear system corresponding to D naught to be the collection of all the devices which are linearly equivalent to D naught and which are effective. So what you wanna do is you wanna associate a set corresponding to this linear system, and you wanna call it as base point set. Now what you wanna do is you wanna take the intersection of the support of all the divisor D that appear in this linear system. Okay, what is the support of a divisor? So if D is summation Ci capital Ci, then support of D is nothing but union of all these Ci, I from 1 to n, I from 1 to n. So what you want to do is you want to take the set theoretic intersection of supports of all the D, where D is coming from the linear system D naught, and you want to call them the base point of this linear system D naught. Now what happens is that the map that you define corresponding to this linear system has indeterminacy exactly on these base points. Indeterminate, has indeterminacy only on the base point. Okay, so you call D naught to be base point free if the base point corresponding to D naught, the base point set corresponding to D naught is empty. So if it is empty, in that case, your P of D naught becomes a morphism. Okay. So this is one of the conditions that like the behavior of D naught actually gives you some information about the behavior of the map corresponding to D naught. I'm sorry if I've been calling this phi D naught morphism since the very first place. It might not always be morphism. It might be just a map. But if your D naught is base point free, in that case, P of D naught becomes a morphism. Well, another such evidence where the behavior of D naught determines or gives some information about phi of D naught is the following. So if D naught is a very ample divisor, in that case, P of D naught is a closed immersion. Okay, good. So let's come back to the proof of the theorem. Recall what were we trying to do? We were trying to show this theorem over here, where x was a smooth projective surface, E was a -1 curve, and we wanted to show the existence of a morphism mu from x to x1, which is birational proper morphism, and some good property should hold, which is that mu becomes a blow-up map, x1 is still smooth, and E is being contracted to a point. So the first task in the proof of this theorem is to really construct mu. And like I said in algebraic geometry, whenever you're trying to construct a morphism or a map, you take help of the linear system. So that brings me to my first step towards proving Castelnuovo's theorem. So basically, we want to find a divisor L, and L, or a complete linear system, L, such that find a divisor, or a complete linear system L, so that the following two properties hold. First, that this thing become a morphism, right? That is, the linear system is base point free. And the other thing that we require is this phi of L satisfies the requirement of the statement. That means the three condition that we say mu holds, phi of L must, like, we need to find an L such that nice things happens. Okay. So note that well, when we say it should satisfy the requirement of the statement, the requirements are as follows. The first requirement is that the map becomes mu should become, or I should not write mu, maybe phi of L should become a birational proper morphism. Then it should be morphism, I've already written up there. And then it should be it should contract E to a point, and then it should be a blow-up map, and x1 should be. So these are the qualities that we require in phi of L, right? Recall that a curve is in the fiber. So a curve will be in the fiber, of phi L if and only if it intersects the divisor in 0. That means you need to find an L, a divisor L, in such a way that L dot E should be equal to 0, but L dot C should not be equal to 0 for any C that is not E. So what you require is that, so if you believe the fact that a curve will be in the fiber of PL if and only if L intersects the divisor in 0, then what you would require is that you only want to contract E and no other curve, right? So what you would require is that phi of L intersected with E should be 0, but L intersected with any other curve C should not be equal to 0, right? So these are the two conditions that we need. Now, a justification to the fact on why, or maybe I'll just leave it for you to think about this, that think about this statement, which is, think about this statement. A curve is in the fiber of PL if and only if intersect the divisor in 0. I'll leave it for you to think. Okay, so let's begin. So the first thing that we require over here is we need to find an L which intersect with E in 0 and with any other curve C. So we shall exploit here the the fact that x is projective, and how would we exploit that? If x is projective, then it implies that there will exist an ample divisor, or I can actually take a very ample divisor. We call it A. Okay. Let's say the intersection of A with E is equal to K. Now, this K is supposed to be greater than 0. Why? Kleiman's amplest. Oh, maybe I'm not writing the spelling correct. Well, since we are on surface, Kleiman's criterion is almost similar to Nakai-Moiseijon criterion. So we are going to use that. So what does it say? It says that A is going to be ample if its intersection with any effective divisor is positive. So A is going to be effective if and only if such a thing happens, that its intersection with any effective curve is going to be greater than 0. Since E is effective, A is ample, so K is supposed to be greater than 0. So what do? We take our L, we define our L to be A plus KE. Now notice that if I take the intersection of this L with E, it's going to be A times E plus A times E times E, which is going to be K minus K equals 0. Correct? And if I take the intersection of this L with any other curve C, that's going to be A times C plus K times E times C, which is going to be greater than 0. Why? Because this is going to be greater than 0. Again, Nakai-Moiseijon theorem. And this is going to be greater than 0. Why? Because these two are effective curves and K is already greater than 0. Right? So this in total is going to be greater than 0. Right? So things seems promising. It seems like a candidate for mu can be the morphism given by the linear system corresponding to the divisor L. And our prediction will turn out to be correct soon. So let's see what is the first thing that we have to do. So we are gonna claim that mu equals phi, which is a morphism corresponding to the complete linear system L, will satisfy the theorem, the statement of the theorem. Okay, let's go back to the statement of the theorem. Let's see what are the expectations from mu, what are the expectations from phi L. The first thing that we require is it should be a morphism, right? The second thing that we require is it should be birational, it should be proper, should contract E, x1 should be smooth, and etc. The first thing that I'm going to attack is the morphism part. So the first thing that we need to show is PL is indeed a morphism. In other words, what I need to show is L as a linear system is base point free. Okay? In order to show that it is base point free, what I would like to do is I would make this claim over here, which is, but before the claim, let me just give another, let me just give another. So let me define Ln to be A plus Ne, where n can be anything from 0, 1 till k. Okay? And what I want to claim for this Ln is that its first cohomology vanishes. Okay? So as you might see, I've taken Ln, so I must be using induction somehow. So how will we prove the claim? We'll use the induction. We shall induct on So for n equals 0, Ln is just A, which is a very ample divisor. So you have the vanishing from Serre's vanishing theorem. Well, you might say, maybe the Serre vanishing might hold for some higher multiple of m, but then you can replace A by MA if needed. Right? It's not going to change the argument. Like you can just take, instead of K, then you can take MK. Like just replace A by some higher multiple of MA and the argument would still work. Okay. So now let's induct on N and assume the result assume the claim holds for N minus claim holds for N minus 1, right? Then consider the short exact sequence given by O of minus E, OX, OE to 0. So then what you want to do is you want to twist this by A plus NE. What do we get? We'll get 0, O, M plus N minus 1E, OX, A plus NE, OE, A plus NE restricted to E to 0, right? Now the short exact sequence will induce the long exact sequence as follows. I'm not going to write the entire long exact sequence, but only a part of it, which contains the first cohomology. See, okay. So now this one will vanish because of the induction. And this third thing over here is nothing but, so E is isomorphic to P1, right? So that implies that this thing is going to be O of P1. And then on Pn, we know that any divisor can be written as O of some number over here, and that number is nothing but the degree of this divisor over here. So it's going to be the degree of divisor over here. It's going to be the intersection of this thing with E, right? So A intersected with E is going to be K here, and then there is going to be minus N in here. So now since K minus N is strictly greater than 0, and we know that OP1 of D is equal to 0 for D strictly greater than 0. H1 of this thing, right, is equal to 0 for D greater than 0. So that gives me that this is going to be equal to 0, right? This is going to imply that H1 of OX ln is indeed going to be equal to 0, hence the claim. Now you might wonder why is the claim needed. It's soon going to be clear. So that brings me to my step 2 towards proving the theorem. Recall, what were we wanting to prove? We were wanting to prove that P of L is a morphism. And for that, what were we trying to do? We were trying to show that this linear system is base point free. Right? Note that the linear system given by the linear system of EA plus n times E is indeed contained inside A plus NE, isn't it? Let's say you take some element from the left hand side. It's going to be of the form D plus NE, where what is D? D is linearly equivalent to A and D is effective, right? Now this gives me that D plus NE is also effective, right? And since D is linearly equivalent to A, D plus NE is linearly equivalent to A plus NE. Well, these two things together gives me that D plus NE indeed belongs to the right hand side, which is A plus, the linear system of A plus NE. Well, what does that say? That says, so now A is ample, right? That means it is base, actually A is very ample. So that means A is base point free. Base BPF. So this implies, I should not write it. So A is very ample. That implies that it is base point free. So that means if there exist base points of this linear system, it should lie on E. If there are any base points corresponding to this linear system, it should better lie on E, because away from E, it is very ample, right? Because it contains this translation of the vector space over here. Okay, so this is, let's say, one thing to think about, which is since A is very base point free, so if there exist base points of the linear system A plus NE, it must lie on E. Okay, so what we shall show is that E, so we shall show that, so we can restrict our attention in finding the base points of that linear system by merely checking on the points of E. So we shall show that corresponding to every point P on E, there exists a D inside the linear system which does not pass through P. Correct? So over here we shall use the claim. Well, did I write this is step 2? This is actually step 1. Okay. So consider the the part of long exact sequence induced by the short exact sequence that we considered before. So we have H0 of OX A plus NE to H0 OE A plus NE to H1 OX A plus N minus 1 E and so on. Now we have seen that H1s are 0, right? Which tells us that this map is a surjective map, right? What is this? These are the global sections of OP1 of the degree of this, which is A minus N. Got to write A, right? So now since this is greater than or equal to 0, we know that whenever we consider OP1 of T, this is nothing but the D degree monomials. This is generated by, these are D degree polynomials in the variable X and Y in here and locally. And then, so what are we trying to show is, so I'm saying that this guy over here has a lot of global sections, a lot of sections, right? so many sections that corresponding every point P on E, there exists a section which does not vanish. Exception is such which does not vanish on P. Right? How would you imagine that? Think about it. Let's say we consider this point 0, 1, 0, right? How can you produce a point? So this is a point inside P2, right? And now I'm saying that, let's say I consider D to be 5. So I can always find a degree 5 polynomial which does not vanish on this. What would be the candidate? I'll take x2 raised to the 5. Now this is a polynomial of degree 5 which does not vanish on this point, right? So this is essentially the same thing I'm saying over here, that when you are on E and you are considering a line bundle given by this thing over here, then it has many global sections, and so many global sections are corresponding to every point. You can find a section which does not vanish on that. Okay, so now the surjectivity will help us. So let's say corresponding to this point P, I can find an S. I can find an S which on which does not vanish on S of P. Then what I would like to do is I would like to lift S under the surjective map, and that would give me a section of A plus NE which does not vanish on P. Well, recall sections of this divisor are going to give me divisors which are linearly equivalent to this divisor and which are effective, right? So we have essentially found out a divisor which does not pass through this point P. Hence, this P cannot lie in the intersection of support of all the divisors which lie inside the linear system of A plus and E. And therefore, this point does not belong to the base point of that thing. Okay. So what does this imply? This implies that P does not belong to the base point of A plus NE. Well, that gives me A plus NE, the linear system is base point free. And this is happening for every n from 0 to k. How wonderful is that? So the morphism that we defined corresponding to L is indeed the map we defined corresponding to this thing is indeed a morphism. Isn't that great? Okay, so the first thing is done. Now, step 2 is to show that the morphism that we have defined over here satisfies the following properties. First of which is the following. You require that P of E should be equal to P inverse of P. So sorry, I might sometimes omit to write L in here. P inverse of P is equal to E. We must show that P is indeed birational and proper. X1 is smooth. P is a blow up of X at P.